Hello my dear students, welcome to IMS Gate Academy. So in this particular series we are going to start the previous year gate questions in the last year like 2023. In this particular year, whichever questions asked in communication subject for EC and IN, so I have selected the special questions which are useful even for the coming gate exam, right? So similarly in the upcoming series we will discuss like year wise. We are starting from 23 and then 22, 21, like that we will discuss few years, right? Yeah, good evening everyone. What is your name? How to pronounce? Yeah, very good evening one and all. So this session is helpful for both the branches, EC and instrumentation. Okay, so in this particular session we are dedicating the questions which are asked in the 2023 year, recent year. Okay, right. And then into yeah, you can cross check once. So how to pronounce your name in short? So can you write your short name so that I will pronounce accordingly? Okay, right. So here in this particular question they have given one message signal m of t which is band limited to, which is a band limited signal having a bandwidth b, having a bandwidth B. So band limited signal means which is centered around 0 frequency, or you can say low frequency signal, among which the maximum frequency of that particular signal is B, and the corresponding signal energy they have mentioned E. Now the question is regarding the signal m of t into cos omega naught t, regarding this particular signal, what is the energy? What is the energy? In this particular question they have mentioned regarding omega naught, which is nothing but 10B. Okay. So you can consider any band limited signal spectrum by considering bandwidth as B. Okay. But for easy understanding, for the timing I will assume m of t as am cos 2 pi fm into t. For the timing I will consider m of t as am cos 2 pi fm into t. Generally we will consider like this, but in this question they have mentioned bandwidth of the message signal as B. So that means, so for the timing I will consider, in place of fm I will consider B, cos 2 pi B into t. Okay. So when you are having either cos signal or sine signal which is having the peak voltage, so in this case you are having the peak voltage as am, right? So by using this one you can write the power of the message signal, which is nothing but peak value square divided by 2. Peak value square divided by 2. I hope you know this formula, right? Whenever you are having sine or cos, so you are having am, so from there you can calculate VRMS. After that you can perform square of that. Okay. So PM is nothing but am square divided by 2. So once if you know the power, you can calculate energy by integrating over a period of time. Integral 0 to t power into dt. Integral p dt is nothing but energy. So according to the given question, energy is nothing but E. So integral 0 to t Pm is am square by 2. So am square by 2 is the constant, right? So we can keep outside the integral. Am square by 2 integral dt is nothing but t. Now you can substitute the limits. So you are getting 0 to t. So from here when you substitute the limits, upper limit minus lower limit, you will get am square by 2 into t minus 0. So from here you can note down the energy of the given message signal is nothing but am square t divided by E. am square t divided by 2. am square t divided by 2. So this is the energy of the given signal. Is it clear, Khawla? Up to this point, is it clear? For the given message signal, for the timing I have considered cos. Similarly, if you want, you can consider sine also, no problem. Okay. I hope it is clear regarding the energy of the signal. Now the question is regarding m of t into cos omega naught t. So can you guess this particular signal represents which signal? Among first chapter we have discussed various modulation techniques. So among which this particular equation belongs to which technique? Any guess? M of t into cos omega naught t. This particular signal represents the equation of which modulation technique? Any guess? Here you are having message signal m of t and here you are having cos omega naught t. So it is just product of two signals, message signal and carrier signal, which is nothing but your DSBSC. So in the DSBSC standard equation, we are having just the product of message signal and carrier signal, right? Yeah. So regarding AM, I hope you know the standard formula regarding the transmitted power in AM. In AM, the power required for transmitting is nothing but PC into 1 plus mu square by 2. PC into 1 plus mu square by 2. So this one you just expand it, you are getting PC plus PC mu square by 2. PC plus PC mu square by 2. So that means here PC is nothing but the carrier power. PC is nothing but carrier power, and PC mu square by 2 is nothing but double sideband power. Double sideband power. So in the AM we are having upper sideband, lower sideband, and at carrier frequency also we are having the signal strength. So accordingly you will get 3 powers. One is carrier power, another one is upper sideband power, lower sideband power. Together we can call it as double sideband power. Okay, double sideband power. So if you want more clearly regarding double sideband, you can mention you will be having both upper sideband and lower sideband. Okay, whereas in DSBSC we are suppressing the carrier power. So whatever the power that is required for transmitting DSBSC, that is distributed to both the sidebands. So that means here this is the standard equation for transmitting AM signal. Now with the help of this understanding, directly you can write power of the DSBSC signal. Power of the DSBSC signal, which is nothing but just this particular power, that's all. PC into mu square by 2. PC into mu square by 2, where PC is nothing but carrier power. Carrier power we can write it as AC square by 2. AC square by 2. And in the modulation technique, in the AM or DSBSC, okay, regarding mu, you are having the standard formula Ka into AM. Here we are doing the modulation with respect to amplitude, right? So where K is nothing but amplitude sensitivity and AM is the peak amplitude of the carrier. So for simple representation for DSBSC, we used to consider Ka value as 1. When you consider Ka value as 1, that time you are getting mu as AM. If you want, you can choose any other Ka value, no problem at all. But accordingly you will get the term. But in order to get the simplified equation for DSBSC, so we used to consider Ka as AM. Ka as 1. So from there you are going to get modulation index as AM. Modulation index as AM. So now in place of mu you can substitute AM. In place of mu you can substitute AM. So that means you are having AM square divided by 2. AM square divided by 2. Right. So from here AC square into AM square divided by 4. AC square into AM square divided by 4. But here if you observe, you are having message signal m of t, which is nothing but AM cos 2 pi FMT or AM cos 2 pi BT. Regarding that, the power is AM square by 2. Okay. So AM square by 2 is nothing but the power of the message signal. Okay. So from here I am just representing, and in this case AC into, generally carrier signal you will be having AC cos 2 pi FCT, but here AC value is 1. So 1 square into AM square, this term I am splitting like this, AM square by 2, and in the denominator you are having 2. So 2 into 2 is nothing but 4, AC square is 1 square, AM square as it is. Now AM square by 2 we can write it as PM or power of the message signal, divided by 2. Okay, I hope it is clear up to this step. Now, so that means for the given product of these two signals, okay, for this particular signal, as of now we got the power. That power is PM by 2. Okay. Now just carefully observe. Earlier for this particular message signal, the power is PM, and since it is constant, when you perform the integration for a constant, Okay, what you are going to get, whatever that constant you are having, that constant is getting multiplied by the time period, right? So with this understanding, now directly you can write, energy of this particular DSBS signal, energy of DSBS signal, which is nothing but Pm by 2 into T, or you can write Pm into T divided by 2. Okay. Okay, so Pm is nothing but Am square by 2, so Pm into T. Okay, so that is nothing but your energy of the original signal. Okay, I am repeating once again. Here Pm is nothing but Am square by 2, so Am square by 2, okay, is nothing but Pm into T. Pm into T is nothing but E. So if you want, in shortcut you can represent like this. Am square by 2 is nothing but Pm into T, right? So that is your energy of the signal, and in the denominator here you are having 2, So now you can observe among the given choices which is satisfying. So here originally you are having m of t, for that bandwidth is b and energy is e. Now the question is regarding m of t into cos omega naught t, what is the energy? So here the answer for this question is option B. Answer is option B. E by 2. Is it clear? Any doubt? I hope it is clear, right? Yeah. I will show the next question, which is asked in GATE EC 2023 for 2 marks. All of you give it a try. So this is a very interesting question which is asked in GATE EC 2023. The question is based on FM signal. So here in this particular question they have given the FM signal. They have given the FM signal like this: x of t is equal to a into cos omega ct, where omega c is nothing but 2 pi f c. So a cos omega ct plus kf integral m of lambda d lambda. So this is standard equation of your FM signal, right? Where m of t is the message signal which is having a bandwidth w. Just like the earlier question, here also regarding the message signal they have mentioned bandwidth as w. In the earlier question they mentioned bandwidth as b. In this question they have mentioned bandwidth as w. Or the bandwidth regarding the message signal, bandwidth or maximum frequency all are same, because it is having low frequency signal, or you can say baseband signal or band limited signal, all are same only, right? It is passed through a non-linear system. It is passed through a non-linear system with output. They have mentioned the relation like this: output of this non-linear system in terms of input they have mentioned like this: 2 into x of t plus 5 into x of t whole square. 5 into x of t whole square, right? Now they have mentioned bt is denote the FM bandwidth. Regarding FM signal is x of t. Regarding this particular signal bandwidth they have mentioned bt. Now the question is the minimum value of omega c required to recover x of t from y of t is. So in this particular y of t equation you are having x of t term and then you are having x square term, okay? After getting y of t, from that particular y of t, in order to extract x of t, what minimum value we can choose regarding omega c, okay, in order to extract x of t from y of t. So that means the reason is the intention behind or here you will get the clarity. It is very simple. You are having initially FM signal, right? Initially you are having FM signal. When you have passed that FM signal through a nonlinear system, you are getting, if you don't have that particular term, here it is whatever FM signal is there, same FM signal, but it is having a scaled factor of 2, that's all, okay? And in addition to that, here you are having x square term. So that means whatever FM signal here you are having, you are getting square of that term, right? Okay, and getting multiplied by 5. Now their intention is very simple. In this particular output, they want to extract only FM signal, only this particular FM signal. In order to extract like that, what minimum value of omega c we have to consider? That is the question. Okay, I hope all of you got the clarity what you are supposed to calculate in this particular question. Okay, right. So here they have given standard FM signal. So regarding, I hope all of you know the formula regarding bandwidth of FM signal. Regarding bandwidth of FM signal. Bandwidth of FM signal, in this question they have mentioned it is bt. So which is nothing but 2 into beta plus 1 into FM, where beta is nothing but modulation index. So 2 into beta is nothing but delta f by FM plus 1 into FM. So multiply FM with both the terms. So you will get 2 into FM will get cancelled. You will get delta f plus FM. So this is the equation for bandwidth. But in this question regarding message signal bandwidth, they have mentioned it as W. So what is the notation they have mentioned, we will follow the same. So that means you are going to get 2 times delta f plus W. 2 times delta f plus W. So this is the bandwidth of wideband FM signal. Okay, bandwidth of wideband FM signal, right? So here you are having resultant bandwidth this much, 2 times delta f plus W. 2 times delta f plus W. Okay. Now regarding x of t is FM signal in this particular question. In this particular question, x of t is your FM signal. So which is having the range of frequencies, centered frequency is omega c. From there towards left hand side, you will be having like this, the minimum frequency, omega c minus, here total bandwidth is bt, so that means here bt by 2 I am considering, to the maximum frequency, omega c plus bt by 2. See, you can easily correlate. See, this is the maximum frequency and this is the minimum frequency. Bandwidth is nothing but difference of maximum frequency and minimum frequency. Omega c will get cancelled. bt by 2 minus of minus bt by 2. So that means from there you are getting 2 times bt by 2. 2 will get cancelled. You are going to get bt. Okay, I hope it is clear. So just like in the AM signal, you are having center frequency of fc and that side frequency fc plus fm, this side is fc minus fm, like that. Okay, so here you are having bandwidth as bt, so that means consider half of that. Okay, omega c minus bt by 2. Similarly here omega c plus bt by 2. When you find the bandwidth from this range of frequencies, you will get bt only. Okay, that is the reason I have mentioned here. For the timing, I am not drawing the spectrum. Okay, but you can easily understand, right? So up to here, whatever we have discussed, that is with respect to your FM signal. That FM signal is nothing but your x of t. So this x of t is FM signal, right? Okay. Now this x of t, they have passed through a nonlinear system like this. Y of t equal to 2 into x of t plus 5 into x of t whole square. Y of t equal to 2 into x of t plus 5 into x of t whole square. 5 into x of t whole square. 2x of t plus 5 into x of t whole square. Okay. So here 2x of t I am keeping as it is. 5 also I am keeping as it is. X of t whole square is nothing but x square of t. So regarding x of t, whatever we have discussed earlier, okay, regarding the range of frequencies, it will be same. Regarding the range of frequencies, it will remain same. Okay. Now we have to focus regarding x square of t, what is the range of frequencies that we are going to get. Okay. So for the timing, I am focusing this one. So here we are having squaring device or square law device or squaring circuit, all are same. Okay. So here x of t is the input, x square of t is the output. Okay. So regarding x of t, that is nothing but FM signal. So FM signal you will be having delta f, and you are having, so in this particular equation if you observe, you are having omega c is there and then frequency deviation delta f you are having. Okay. So yeah, and we have calculated just now regarding bandwidth bt. So whenever you are passing any FM signal through a non-linear device, okay, for the timing here regarding that non-linear device, they have given the relation like this. Regarding this part, if you observe, it is a linear only, so there won't be any modification. Whatever delta f you are having, same thing. Whatever omega c you are having, same thing. Whatever bandwidth you are having, same thing. Okay, right. Regarding x square of t, how the differ will come, okay, that we are focusing now. So here square law device you are having. So if you are having delta f for x of t, so whatever power here you are having, that power you have to consider with that scaling factor. So here numerator you are having power 2, right? So now whatever the values here you are having regarding delta f, it will be getting scaled version of 2, or you can say that this particular value is getting multiplied by 2. Similarly, if you are having power n, it will be getting multiplied by n times, like that. Okay. So first let us focus regarding these two. So delta f, initially we are having So here after passing through square law device, I am assuming that delta f dash. So which is nothing but 2 times delta f. 2 times delta f. Okay. Similarly, omega c. Omega c, here I am considering omega c dash. So that is also becoming n times. Here n is nothing but 2. 2 times omega c. 2 times omega c. Okay. Now regarding bandwidth here. So for the timing I am considering as bt dash. So here we got this formula, right? So in this particular formula regarding delta f, now there is a modification. Regarding delta f there is a modification. Regarding w there won't be any modification. Whenever you are passing any FM signal through a nonlinear device, okay, only delta f and FM won't change. Okay, here FM you are having W, so that will remain same. Okay, so whatever, when you take the ratio of these two, that is nothing but beta equal to delta f by W, right? So here beta dash, here delta f dash divided by W. Delta f dash divided by W. So where delta f dash in this case it is 2 times delta f divided by W. So delta f by W, just now we have mentioned beta. So that means here you are getting 2 times beta. So that means what is your observation? Whenever we are passing any FM signal through a nonlinear device, the frequency deviation is going to get scaled by a factor of n times. Whatever earlier frequency deviation you are having, it is getting multiplied by n times. Similarly, the carrier frequency also getting scaled by a factor of n times. Okay, and here regarding modulation index, that is the main purpose. Only we want to increase or multiply the original beta value by n times. So for that reason we are passing through the square law device as any power n circuit. But in that process, now carefully observe, here numerator you are having delta f. The relation between beta and delta f is directly proportional. If beta value is getting scaled by a factor n, obviously delta f dash is also scaled by a factor n, right? So that means here there is no change in the modulating signal frequency. I hope it is clear. But in this process, whatever in this overall term, whatever carrier frequency you are having, this overall term is getting multiplied by n times. So in that process you are going to get all this whatever conclusion points we have mentioned. Okay, right. So that is the reason here earlier you are having omega c, that is becoming n times omega c. Here n is nothing but 2. Okay. Now with this understanding, okay, so you are having bandwidth formula for the FM signal like this, 2 into delta f plus W. Now whatever the modification values we got, with that we will consider. Okay, so bandwidth equal to 2 times. So in this case it is delta f dash plus FM. FM is nothing but W. 2 into delta f plus W, but here delta f modification is there, and regarding W there is no modification. Okay, now whatever delta f dash we got, just substitute. Delta f dash we got 2 times delta f plus W. Okay, so multiply 2 with both the terms, so that means you are getting 4 delta f plus 2W. 4 delta f plus 2W. Now I am just representing in this particular fashion. Here you got 2 into delta f plus W. So in a similar way, if you write that entire term as it is, 2 into delta f plus W. So up to here what you got? 2 into W. Yes, that is matching here exactly. Here you are having 2 delta f, but here you are having 4 delta f. That means 2 delta f extra is there. So that I am representing here. 2 delta f here. Okay, so this delta f plus W is nothing but the bandwidth of your FM signal x of t. Okay, 2 into delta f plus w is nothing but bandwidth of FM signal BT. Okay, yeah, so here 2 won't come, just 1 second. This entire term is BT. This entire term is BT. 2 into delta f plus w is nothing but BT. After that you are having 2 times delta f. 2 times delta f. So this is your BT dash. Now calculate half of this one. Calculate half of this one. So that means BT will become half and this term will become half. So that means you are going to get delta f. Delta f. Okay. I hope it is clear why I have done like that. Here you got BT dash. BT dash. Now I have divided overall term with 2. BT dash by 2, which is nothing but BT by 2 plus delta f. Now you can easily understand. Here earlier you got BT, right? The bandwidth of the original FM signal x of t. Now regarding x of t, the range of frequencies omega c minus BT by 2 to omega c plus BT by 2. This is the range of frequency. Similarly, now the range of frequencies that you are going to get omega c dash minus BT dash by 2 to omega c dash plus BT dash by 2. That is the reason I have calculated this particular equation, but whatever the right hand side terms you are getting, I have represented in terms of the previous, so that we can do the correlation according to our requirement. Okay. So now regarding x square of t, okay, I will write like this. Okay, whatever the equation here you are having regarding y of t equal to 5 into x of t plus, sorry, y of t equal to 2 into x of t plus 5 into x square of t. 2 into x of t plus 5 into x square of t. Okay. So regarding x of t, you got earlier, this is the range of frequencies, right? Omega c minus BT by 2 to omega c plus BT by 2. Omega c minus BT by 2 to omega c plus BT by 2. Okay. Spectrum on the frequency axis, you will get the range of frequencies remains same. Regarding the amplitude or signal strength, there slightly variation will be there. Okay, that we no need to bother, because here the question is regarding the minimum value of omega c they are asking in order to recover x of t from y of t. Okay, so in x of t we are having this range of frequencies. Similarly in y of t also, regarding the first term we are having the same range of frequencies. Okay, this is our requirement. We have to extract this range of frequencies. Okay, now in this process, okay, we got regarding x of t as it is. Now regarding x square of t, you follow similar notation. Here omega c you are having, in place of that you will get omega c dash minus here BT is there, BT dash by 2. Okay, similarly omega c dash plus BT dash by 2. Omega c dash plus BT dash by 2, right? Here omega c dash we got 2 times omega c. So substitute now. Omega c dash is nothing but 2 omega c minus BT dash by 2. Just now we got this expression, you can substitute BT by 2 minus BT by 2 plus delta f. Similarly, you can substitute here also. Omega c dash same, 2 times omega c plus BT dash by 2 is nothing but this entire term. So that means you are going to have BT by 2 plus delta f. Right? Now, from here, just multiply these two terms with minus. You will get 2 omega c minus BT by 2 minus delta f. 2 omega c plus BT by 2 plus delta f. right? So this is the range of frequencies regarding x square of t. This is the range of frequencies regarding x of t. Now our requirement is we have to extract only x of t part. Okay, so regarding that, okay, they are asking what should be the omega c value. Okay, now if you carefully observe this particular range of frequencies, it is centered around omega c. Omega c is the center frequency. Just for your reference, I am mentioning here. So here you are having omega c, and this is the upper frequency you are having here, omega c plus beta t by 2, and similarly omega c minus beta t by 2 here you are having. Similarly on this frequency spectrum, here these two frequencies are centered around 2 omega c. Say for example I am considering this is your 2 omega c. Okay, so this overall term is when compared to 2 omega c, this overall term is what? Less. So obvious that will be here, right? Similarly, when compared to omega c, this overall term is greater, right? So this particular frequency you will be having, here. Now you are having like two spectrums. One spectrum is regarding x of t, another spectrum regarding x square of t. Okay. Now here regarding the first spectrum, when you want to recover, okay, so regarding the first spectrum, this is the maximum frequency. Okay, if you want, you can pass this particular spectrum through a band pass filter so that you can extract this particular information. So that means you are rejecting other one, other part. Okay, right. Now if you carefully observe regarding this particular frequency, range of frequencies, so this is the starting frequency. Okay, so when you are choosing band pass filter, okay, which is having the range of frequencies here, that means automatically this was eliminated. Okay, only you are allowing only regarding x of t. In that way we can recover, right? So here regarding these two, if you want to give the relation, you can give the relation that this particular frequency should not present anywhere here. So that means obvious this particular frequency can be the starting frequency of here, or could be anywhere just after this one. Yeah, Shiva, you are correct that multiplication with 2 pi you can do later, okay, but for the timing I am just representing in the normal way. Okay. Okay, right. So here when you look at these two spectrums, okay, so this particular frequency should be either equal to this one or greater than this one. Okay, so that is a condition. So 2 omega c minus bt by 2 minus delta f should be greater than or equal to omega c plus bt by 2. Okay, so from here omega c you bring to the left hand side, it will become minus 2 minus 1 is 1. Then other two terms you bring to the other side. Okay, so here minus bt by 2, it will become positive. So that means 2 times bt by 2. So 2 will get cancelled. Minus delta f will become plus delta f. So from here you are getting omega c greater than or equal to bt plus delta f. Okay, so here bt is nothing but what? Earlier we got bt as 2 times delta f plus fm. This one you can substitute now. bt as 2 times delta f plus fm. Okay, where fm is nothing but w. 2 into delta f plus w plus delta f, delta f. So from here, yeah, just multiply 2 with these two terms, you will get 2 delta f plus 2w plus delta f. Now you can add these two, 2 plus 1, 3 delta f plus 2w, 2w. So up to here you got like this, up to here you got like this. Now if you observe, left hand side you are having omega c, right hand side you are having delta f term and w, delta f term and w you are having. Okay. So when you look at choices, regarding minimum value of omega c they are asking. Okay. So that means left hand side whatever we have considered omega c, that is correct only, but right hand side if you observe, you are having in all the options you are having bt term. Bt term is there. In addition to bt, you are having like w in few choices. In other two choices, you are not having w. Okay. Right. So here somehow or other we have to express this particular overall term in terms of bt. Okay. So regarding bt, we have mentioned delta f plus w. Right. So what is the relation here we got? Okay. We have to write in terms of bt. So that means here omega c greater than or equal to, here 3 into, regarding bt you are having delta f plus w, right? Delta f plus w you are having, sorry, bt is nothing but 2 into delta f plus w. Okay. So 3 I am keeping as it is, I am multiplying and dividing with 2. So say for example, for easy understanding, whatever bt you are having, just copy as it is, 2 into delta f plus w, 2 into delta f plus w. So somehow or other if you are getting like this expression, you can write that expression as bt. That is my requirement, because when you look at the choices, in all the choices you are having bt term. Okay. So here now in order to get like this, okay, since you have multiplied with 2, I have divided with 2. So 2 will get cancelled. Okay. After that 3 into delta f, yes, it is matching. Next, here 2 will get cancelled, 3 into w you are getting, but here you are having 2w. So what we have to do, we have to subtract w. Now you can equate both, whether both are matching or not. 2 will get cancelled, 3 times delta f, yes, it is matching. After that 3w minus w, which is nothing but 2w. Now this entire expression you can write bt, 3 by 2 bt minus w. So from here you are getting the relation like this, omega c greater than or equal to 3 by 2 times bt minus w, where bt is nothing but bandwidth of FM signal, where w is nothing but bandwidth of message signal, So in general, the bandwidth of FM signal you will be having very large when compared to bandwidth of message signal. In general, message signal bandwidth you will be having in the order of kilohertz, whereas bandwidth of FM signal you will be having very high when compared to that kilohertz order, right? So by considering like that, for making approximation only, you can neglect bandwidth of message signal. So from there you are going to get 3 by 2 bt. Okay. So from here, if you want regarding omega c, you can consider this value, or you can consider any value when compared to this one, it should be greater, right? So obviously omega c minimum will be 3 by 2 bt. So the answer for this question is option B, 3 by 2 bt. Okay, all of you try the next question. This is the question asked in GATE instrumentation in the year 2023 for 1 mark. This simple question, all of you give a try. Yeah. So here this is the question based on the random variables. Here they have mentioned x is a discrete random variable which takes 3 values 0, 1, 2. So regarding that, you are having 3 random variables, okay, but among those 3 random variables they have given probabilities only for 2. Okay, they have given probabilities only for 2, right? So first of all, note down the corresponding probabilities given. Probability of x equal to 0, they have mentioned as 0.25. Okay, probability of x equal to 1, they have given as 0.5. Now you are having one more symbol 2, but they haven't given the probability. But you know that when you are having suppose 3 random variables, so sum of all the probabilities equal to 1. So you can calculate this value by subtracting after performing addition of these two, that value you can subtract from 1. Okay, so directly I am writing here 1 minus of 0.25 plus 0.5. Okay, so 0.25 plus 0.5 is 0.75. 1 minus 0.75 is 0.25. Okay, or directly by observing these two, 0.25 plus 0.5 you are getting 0.75. By adding with which value you are going to get resultant value as 1. So that is nothing but 0.25. So in that way also you can directly guess. Okay, so now you got all the probabilities for 0, 1, 2. You are having the corresponding probabilities, and here this is the expectation operator that you know. Now the question is e of x minus e of x square. That value they are asking, right? So first of all, let us calculate expectation of x. So expectation of x is nothing but, if it is a continuous random variable, we could have used the integration term, but here it is a discrete random variable, so in place of integration you can use sigma, summation. So here summation operation I am using, I equal to 1 to n. So here expectation of x is nothing but x into here probabilities, probability of x equal to x. Okay, so in this case you are having 3 variables, so that means this particular product you have to perform only for 3 cases, that's all. Okay, so here the first variable is 0, the corresponding probability is 0.25, plus second variable is 1, the corresponding probability is 0.5, plus the third variable is 2 and the corresponding probability is 0.25. So here 0 into anything is 0, 1 into 0.5 is nothing but 0.5, plus 2 into 0.25 you can write as 0.5. So 0.5 plus 0.5 is nothing but 1. So this is the expectation of x, Now let us calculate expectation of x square, which is nothing but, once again, sigma summation over I equal to 1 to n. Here x square is there, so that means xi square into probability of x equal to xi. So just like earlier, here also you will get 3 cases. Okay, first variable is 0. So obviously when you are performing square, 0, 0 square 0, 0 into anything 0. So instead of writing the complete term, I have represented 0. Now the second term you are having 1, so square of 1 into the corresponding probability. Probability is 0.5, plus one more variable is 2, square of 2 into the corresponding probability 0.25. Okay, so 1 square is 1, 1 into 0.5 is 0.5, plus 2 square is 4, 0.25 you can write as 1 by 4, 4 will get cancelled. So you are getting 1 plus 0.5, that is nothing but 1.5. So you got expectation of x is 1, expectation of x square is 1.5. Now they are asking the difference of these two, expectation of x minus expectation of x square, expectation of x minus expectation of x square they are asking. So here expectation of x we got 1, minus expectation of x square just now we got 1.5. So 1 minus 1.5 is minus 0.5. So the answer for this question is minus 0.5. All of you give a try. Next question is very interesting and it is a simple question only. Okay, I am not giving the timer, so all of you give a try. This is a question asked in GATE EC 2023 for 1 mark. It is MSQ. Here they have mentioned that for a real signal, which are the following is or E/R valid power spectral densities. Okay, here in 2 choices they have given the equations. In another 2 choices they have given the power spectral density. Okay, power spectral density waveforms they have given. So among these four you have to identify which are really valid regarding power spectral density. All of you give a try. So first you can verify these two, whether those are valid power spectral density or not, and then you can verify regarding these two also. Yes, if you observe regarding the power spectral density, I hope all of you know that here they have mentioned the input signal is real signal. Okay, for the real signal they are asking the corresponding power spectral density. I hope all of you know this property. I hope all of you know this property. The power spectral density, suppose here for x they have mentioned, right? So Sx of omega should be equal to Sx of minus omega. So that means it is an even function, right? So that means power spectral density is an even function. Power spectral density is an even function. So first of all you can verify with the help of this logic. Okay, Sx of omega should be equal to Sx of minus omega, right? Similarly, if they are giving in terms of f, accordingly minus f. Okay, so here in option A, if you observe, in option A already they have given Sx of omega. Now in place of omega, if you are considering, in place of omega if you are considering minus omega, so just in place of omega you substitute minus omega, that's all. 2 by 9 plus omega, in place of omega I am keeping minus omega, right? So that means here square of minus term you will get obviously positive. So that means you are going to get 9 plus omega square, right? 2 by 9 plus omega square. It is exactly matching to original function, right? So that means it is an even function. It is satisfying. So that means it is a valid density function. Option A is valid. Similarly, option B. Option B you can verify Sx of minus omega. Sx of minus omega. In place of omega you have to substitute minus omega. So here minus omega whole square into cos square minus omega. Okay, here minus omega whole square, that means it will become positive. Cos square, cos function is even function, so cos square of minus omega directly you can write cos square omega. Okay, so whatever the original function we are having, after applying in place of omega when you substitute minus omega you are getting exactly, right? So this is also valid function. This is also valid function. Okay, power spectral density is an even function. With the help of that, when you have verified option A, option B, both are satisfying. So that means these two are valid. Now let us verify option C, option D, whether those are satisfying or not. So here just by looking at this particular waveform, say for example here, okay, here some instant I am considering. So for this omega you are having what? The value as 1. So the corresponding minus omega you will be having here. Say for example this is omega naught. Okay, here you will be having minus omega naught, but here the corresponding power spectral density you are having minus 1. Both are not matching. Both are not matching. So it is not valid power spectral density. This is not a valid power spectral density. Okay, and similarly here also if you observe, here say for example I am considering omega naught, for that you are having 1, but what about for minus omega naught? You should have 1, but here you are having 0, 0. So here also it is not satisfying. This is also not a valid PSD. Not a valid PSD. Okay, so only option A, option B are satisfying. So the answers for this question is only option A and option B. Option A and option B are the valid power spectral densities. This is a MSQ. So you have to choose, because in this question two choices are correct, you have to choose both the correct options. If you say for example you have chosen only option A, you haven't chosen option B, so you won't get any partial marking, you won't get any negative marking also. Okay, so for this question if you have to get the marks, so you have to choose both option A and option B. Both option A and option B you have to choose. Right, now the last question. This is the question asked in GATE EC 2023 for 2 marks. So here in this question you are having x of t is a white Gaussian noise. The corresponding power spectral density they have given 1/2 watt per Hz. 1/2 watt per Hz. Okay, so that means it is a double-sided power spectral density. Just by looking at this value you will come to know whether it is single side or double side. Okay, 1/2 watt per Hz. And now the question is, if x of t is input to an LTI system with impulse response, e power minus t u of t, e power minus t u of t. This is the impulse response, okay, of that LTI system. Now the question is average power of the system output they are asking, average power of the system output. Okay, I hope all of you know this particular formula. Say for example, for any LTI system, for any LTI system, if you are giving input as x of t and LTI system is having an impulse response h of t and output you will get y of t, right. So regarding input signal, the power spectral density is, say for example, I am mentioning as Sx of omega. This is the power spectral density of input, okay, or if you want you can write in terms of f, no problem. Sx of f, this is the power spectral density at the input side, and you want to calculate the power spectral density at the output side, and the Laplace transform will be having the transfer function h of f, okay. Now regarding the output power spectral density, the formula is input power spectral density into magnitude of h of f whole square, magnitude of h of f whole square. So this is the power spectral density, this is the power spectral density at the output side, okay. Now in the question they have mentioned the power spectral density is 1/2 watt per H, 1/2 watt per H, okay, into magnitude of h of f whole square, okay. Here f varies from minus infinity to infinity, here f exists from minus infinity to infinity, sorry, minus infinity to infinity, okay. So this is the output power spectral density we are having, but they are not asking output power spectral density. What they are asking? They are asking average power, average power they are asking, average power of the system output, okay. So average power how we can get? It is very simple. Power spectral density you are having, right? So if you are performing the integration of the power spectral density, from there you are going to get power, okay. So here average power of the system output, that is nothing but Py. So you will get by performing the integration from minus infinity to infinity the output power spectral density with respect to df. When you perform the integration of power spectral density, from there you will get the power. Now substitute integral minus infinity to infinity, Sy of f is nothing but 1/2 into 1/2 is the constant I am keeping outside the integral, modulus h of f whole square, modulus h of f whole square df, right. So here 1/2 integral minus infinity to infinity. So here you are having magnitude of transfer function whole square, that one you can write it as in time domain h square of t you can write by using Pascal's relation, right, h square of t dt. So based on convenience, either you can, if you are able to solve, you can solve in the with the help of transfer function only, but whenever you are having magnitude of transfer function whole square, that one you can write it as h square of t, time domain signal, okay. So here actually you have to perform in the frequency domain integration, but that one you can convert into time domain by using Pascal's relation. Now if you observe the question, they have given the impulse response in the time domain, impulse response they have given, right, h of t, e power minus t u of t, e power minus t u of t. Since you are having u of t, it exists from 0 onwards only, from t equal 0 instant onwards towards on the positive t axis, right, 0 to infinity, 0 to infinity you are having e power minus t, e power minus t. So now you have to change the limits, integral 0 to infinity, here e power minus t you are having, e power minus t whole square dt, e power minus t whole square dt. So you are having the formula like a power m whole power n, which is nothing but a power mn, a power mn. So 1/2 integral 0 to infinity e power minus 2t dt. Now you can perform the integration, Py is equal to 1/2 is a constant, you can keep as it is, e power minus x integration you will get e power minus x, but here x is nothing but what, minus 2t, okay, e power minus x integration you will get e power minus x divided by minus 1, okay. Here x is nothing but 2t, So derivative of 2t is nothing but 2. See, if you are having simply like e power x dx, integration is nothing but e power x, okay, divided by 1. But here you are having e power minus 2t dt. So integration of e power minus 2t, you will get e power minus 2t, and then perform the derivative of this power term, minus 2t derivative, you will get minus 2. Here limits are 0 to infinity, 0 to infinity. So substitute the limits, 1 by 2, here you are having minus 2 as it is I am keeping. Substitute upper limit, e power minus infinity is 0, minus e power 0 is nothing but 1. Okay, so 0 minus 1 is nothing but minus 1 divided by 2 into minus 2. So here minus will get cancelled. You are getting 1 by 4, which is nothing but 0.25. Units are watts, 0.25 watt. So in this particular session, we have discussed variety of gate questions which are asked in the GATE 2023, which are asked in EC and instrumentation. We have discussed variety of questions which are helpful for your coming GATE exam, right? I hope all of you liked the methods, and I hope all of you got the enlightenment how to solve these type of questions. Okay, some of the questions are dead easy, but some of the questions are very lengthy, right? So whenever, because communication system subject is a very, with respect to syllabus wise, it is a vast, and even some concept wise also there are so many concepts are there, right? So some questions definitely you can solve in less time, but some questions definitely will take more time. But whenever you are getting such kind of lengthy questions, or especially the questions which will take more time for solving the questions in the GATE exam, you have to change your strategy. You should be like, you have to focus whichever questions you can solve in less time, you can focus those questions in the beginning, and whichever questions take more time, those questions you can focus at last, okay, instead of focusing at first. Because in the initially, if you are focusing not only for communication system subject, just like even in the EDC, analog, EMT also, some questions will be lengthy questions or difficult questions which may take, concept wise it is not at all difficult, but for solving the question definitely it may take time, right? So whichever questions you are identifying like that, don't try to solve those questions in the initial time. If you are solving such kind of questions in the initial, most of the time got stuck there only, okay? So you are having very limited time, but in that limited time you have to attempt more number of questions correctly. Later you will get under 10s, right? So that's why you have to play very smartly during your GATE exam. Whichever questions you can easily solve in less time, focus on those questions in the beginning, and whichever questions may take more time, those questions you can try later, so that definitely you can try to attempt maximum number of questions, try to get the correct answers, right? So in that way you have to balance with respect to accuracy and with respect to speed during your GATE exam, right? So I hope all of you liked a lot regarding this particular session. So in tomorrow's session, we'll discuss GATE 2022 questions which are asked in EC and instrumentation branch. Whichever questions, okay, I will select very good questions which are helpful for your coming GATE exam also, right? So thank you everyone. We'll meet you all in tomorrow's session. Bye bye.